Hello everyone. Today we will talk about the role of artificial intelligence in physics. So this is the overview of my talk. This slides summarizes the central idea of the presentation. Now artificial intelligence allows us to model complex physical systems and using data-driven approaches, which is especially useful when traditional analytical methods become difficult or computationally expensive. So the key capabilities are AI can handle high-dimensional problems, process large data sets efficiently, and is applicable across multiple areas of physics. However, some important challenges are there. AI models are often difficult to interpret. Results may not always be reproducible, and uncertainty estimations remains a major issue. So while AI is powerful, it must be used carefully in scientific contexts. So the motivation behind AI is that in physics it comes from the increasing complexity of modern problems. Traditional methods such as perturbation theory or deterministic numerical solvers work well for the simpler system but struggle with the higher dimensional or the problems that use a lot of data. Therefore, we need scalable computation approaches that can efficiently model such systems, and this is where AI becomes useful. So, AI represents a shift in how we approach towards physical problems. Instead of relying on the first principle equations, we now combine them with a data driven learning. This allows us to capture complex nonlinear relationships, build hybrid models that integrate physics and machine learning, and also improves predictive accuracy, especially in systems where exact solutions are difficult. So this is the basic structure of physics informed neural network. So it includes the input layer, the hidden layer, output layer, and these lines are the weighted links that send the signals. So physics informed neural network trained neural networks using both data and the physical laws, ensuring the solution is accurate and physically consistent. Now, physics-informed neural network loss function is calculated as loss total is equal to loss data plus lambda times loss physics. Here, data loss measures how well the model fits known data. Physics loss measures how well the model satisfies physical laws. And lambda is the weighing parameter. It controls balance between fitting data and also satisfies the physics. So important insight here is that if lambda is too small, it ignores the physics, and if it is too large, it ignores the data. So the neural network is trained so that it fits the data and satisfies the differential equation everywhere, and also ensures physical consistency. Therefore, physics informed neural network it converts solving differential equation into an optimization problem. Now we want here to approximate the true physical solution using a neural network. This is our goal. So total loss structure is calculated as data loss plus physics loss. Here data loss ensures agreement with known observations, and physics loss ensures governing equations is satisfied. This formulation ensures that learned solution is both data consistent and physically valid. In traditional methods, we solve a partial differential equation numerically by using finite difference method, Runge, Kutta, etc. But by using physics informed neural networks, these methods, we obtain the solution using optimization procedures. The relationship between AI and physics is not one directional, it is bidirectional. On the one side, AI helps physics by solving problems, analyzing data, and perform simulations. On the other side, physics contributes to AI through theoretical frameworks such as statistical mechanics, variational principles, and dynamical systems. These concepts help us understand and improve machine learning algorithms. Now coming towards the theoretical foundations. So the statistical mechanics and learning it is a strong analogy between machine learning and statistical physics. In statistical mechanics, physical system evolves towards a state of minimum energy or maximum entropy. It depends on the formulation. Similarly, in machine learning, a model learns by minimizing a loss function. Now, the loss function is calculated by 1 upon n summation y minus fxi theta whole square, where theta is the parameters of the neural network, fxi theta are the model predictions, y is the actual data, y minus fxi whole square it is the error, and summed over all the data points it is a total error. So basically this is a mean squared error. So training a neural network can be viewed as an energy minimization process. This loss function behaves as an energy function. Training the neural network is equivalent to finding the parameter configuration that minimizes this energy. So we can compare both, like physics means minimizing free energy and machine learning minimizing the loss function. Now, many AI methods are based on the optimization, which is closely related to variation principles. In physics, we often find solution by minimizing an energy function. Similarly, in AI, we optimize a loss function. So, example includes variational autoencoders and energy-based models. Now, coming towards the application in physics, in high energy physics and nuclear physics, AI plays a crucial role in analyzing large experimental data sets. Application includes event reconstruction, particle identification, signal and background separation. AI helps in predicting nuclear reaction properties of nuclei by learning complex pattern in data, thereby reducing the complexities in calculation and simulations. Now, in the condensed matter and material sciences, AI accelerates material discoveries. It helps predict the properties of the materials, classify different phases and approximate electronic structures. This significantly reduces the time required for designing new materials. In astrophysics and geophysics, AI is used to process massive observational data. The examples are galaxy classification, detection of gravitational waves, climate modeling, seismic data analysis. AI enables faster and more accurate interpretation of the complex data. Now, challenges are interpretability. One major issue with AI model is that their black box nature. Even though they provide accurate predictions, it is often difficult to understand how they arrive at those results. This limits their usefulness in scientific research, where interpretability is essential. Reproducibility and robustness. Another challenge is reproducibility. AI model can be sensitive to training data, hyperparameters. Small changes can lead to different results, which makes standardization and validation very important. Now, uncertainty means in physics it is crucial to quantify uncertainty. However, many AI models do not provide reliable uncertainty estimations. Towards the future, AI in physics requires strong computational support. This includes high performance computing systems, large scale data storage, efficient algorithms. Without this infrastructure, large scale AI applications are not feasible. The future of this field is highly interdisciplinary. It requires knowledge of physics, machine learning, mathematics, data science. Training researchers in all these areas is essential for the progress. AI is no longer just a tool. It is becoming a paradigm for scientific discovery. It enables surrogate modeling, solving inverse problems, discovering underlying physical laws from data. This represents a major shift in how science is conducted. So to conclude, AI is transforming physics by enabling efficient modeling of complex systems and expanding research possibilities. However, challenges such as interpretability, robustness, and uncertainty must be addressed. Future progress depends on developing physical, consistent, and reliable AI frameworks. So, these are some key references that form the foundation of this work. Thank you.